Go for it.
Awesome. Hi, my name is Jack Atlanta, and for my 20% project, I performed research on the human hand and eventually designed and built a robotic hand that can emulate the human hand. I really wanted to do this project, and I was inspired early in storm season in the fall. In two emergency briefings after Hurricane Irma, there were sign language translators in these briefings to translate what the official was saying to those who can't hear. And someone noticed that in both of these instances, the sign language interpreter was translating incorrectly. In one instance, over here, the man was incompetent because he didn't know the emergency dialogue. In the other instance, there was a woman who was simply an imposter. And I said, this is horrible. Information mistranslated in a critical situation like this could be disastrous. So I decided to build a robotic hand that could perform sign language. And to do this, I performed research on the human hand to make a biologically similar model. And finally, and this ties back into the biology, I wanted to make a realistic, versatile human hand, not something that most people have seen where it uses axles and other things that aren't found in human biology, but a very authentic sort of robotic hand. Over the course of the project, I performed research on the human hand, and I'll go over the anatomy. I also designed and developed a human hand and fingers using SketchUp to 3D model all the pieces and then a 3D printer to print all the parts. And I finally put it all together using analogous structures and servo motors to actuate all of the joints. To start with, I'll go over the anatomy. Some basic terms that you would probably need to know for this presentation are flexion and extension. Extension is a straightened joint. Flexion is a bent joint. Adduction and abduction, that's left-right movement of the wrist. Extension and flexion are bending forward and backwards of the wrist. The bone structure of the hand is composed of three sections. The first section is the carpus. The carpus is the wrist. It allows for abduction and adduction of the wrist and extension and flexion. The next section of the hand is the metacarpus. Metacarpus is composed of 5 bones. These 5 bones make up the palm area and allow for some movement of the thumb. The final section of the hand is the phalanges, composed of 3 bones per finger and 2 for the thumb. These bones allow for flexion and extension of each joint and are mostly responsible for grabbing and gripping motions of the hand. The wrist structure, the carpus, is composed of 2 layers, the first and second layer of the carpus. The first layer of the carpus comes in contact with the radius and ulna, the forearm bones, and these 2 bones are the main, are responsible for left-right movement of the hand, so abduction and adduction. The second row of carpal bones here is responsible for flexion and extension of the wrist with some assistance from the metacarpal bones. Another important structure is the muscle and tendon structure. For the most part, the muscle structure is located in the forearm. However, the precise movements that are required for sign language, for instance, are located in the interosseous muscles. These are tiny muscles located in 2 layers in your palm. These 2 layers perform extension and flexion of each of the fingers and their joints. So if you want to get precise movements, you would use these muscles. These are the muscles that I emulated for my robotic hand. The layers of muscle in the forearm, it's composed of 3 layers. The first layer is the superficial layer. This layer is mainly responsible for the adduction and abduction of the wrist and extension and flexion of the wrist. The second layer is the intermediate layer. For the most part, this is composed of 1 main muscle. This muscle controls most of the powerful extension and flexion of all of the fingers, which is why when you bend one finger, some of your fingers bend with it. They're all attached to the same muscle, and tendons connecting that muscle to your fingers all move when you try to flex one finger. The final layer is the deep layer. For the most part, this moves the thumb and the metacarpal bone that makes up the thumb. Another really important structure is ligaments, tendons, and cartilage. These were very important in my robotic hand. The ligaments, probably one of the most critical parts, allow for structure and strength of your bone structure, meanwhile providing some flexibility so that you do have mobility in your wrist and fingers. The tendons allow for translation of movement from muscle is located in your forearm all the way to the tip of your finger. This is also very important because you can't necessarily fit muscles all the way up into your fingers, so you need a way to translate the motion. The final structure that's very important is cartilage. Cartilage is located in between each of your joints, and this allows for smooth movement of the joints, including preventing like arthritis. Arthritis is caused by the degrading of cartilage, and that sort of scenario could, if my cartilage didn't work correctly, could break my fingers. They wouldn't be able to move correctly, so I need to prevent that and use good cartilage. After I finished my research, I began to design and develop my fingers. I used SketchUp as the 3D modeling tool to design my fingers, and I printed them using a Zortrax M200 printer. The basic design of my fingers would be a ball and socket design, very similar to the bone structure of the human hand, with a string running from the tip of each joint. Here I have one joint laid out, and the string would run from the tip of the joint all the way to the back of the finger, where it would be pulled by a servo motor to actuate the joint. Here I have a bent model, and as the finger bends, the string gets shorter, which is why the servo, when it pulls it, it will actually bend the finger as well. Here is what the human finger would look like in such a scenario. The tendon that starts at the tip of the finger gets pulled by a muscle located in either the interosseous muscles or the forearm, and as that muscle contracts, it pulls the tendon and bending the joint. When I was designing my fingers, I had my first 3 set of revisions of the finger consisted mostly of adding structure to the finger, not necessarily mobility just yet. In my first finger, this, as I said, when I used cartilage and various other structures, if that degrades, you end up with something like this. My finger was bent all over the place. I could horizontally and vertically dislocate almost effortlessly. So I began to add structures that were similar to the human hand to improve this. I first added ligaments on the side of the finger to provide structure and prevent horizontal or vertical dislocation. I also added a positive stop, which is kind of apparent in human bone structure, as there's a similar structure between each joint to prevent hyperextension. In my next revisions of the finger.
Keep going.
Okay.
Skip past that one slide.
Skip past it?
Yeah.
Okay.
Let's see if that
I'm going
works.
to skip past that one too because that one crashes. So, in my next set of 6 revisions, I first started to add mobility to the finger, changing the way the joint was structured. And in my next set of 3 revs, I added humanoid structures and characteristics. After I completed a design for the finger, I could analyze the analogous structures that I had utilized. My first analogous structure I utilized was dental rubber bands. These rubber bands I used kind of as ligaments to provide structure in the finger between the joints. That's similar to what the human hand uses ligaments to wrap around the joints. Another analogous structure I used was Teflon tape. Initially, I was using this to act as a cartilage and prevent grinding of the 3D parts as they bent. But as I soon realized that the tape actually just tore up and made a mess. And this is kind of why if cartilage fails, you end up with poorly moving joints. As in my scenario, my joints started to move poorly because the Teflon tape ripped up. And I eventually replaced it with a different lubrication system that I use now. Another analogous structure I used was tendons and 6-pound or 30-pound line for the tendon structure. I used these to attach the different parts of the finger to the servo motors located in the palm of the hand. I had designed for all of my fingers, the thumb, and I started to move into the robotics and mechanical aspects of this project. For my locomotion of all of the individual joints, I used servo motors in 2 forms. A 9-gram servo, which I would use to actuate each of the individual joints of the hand, and a 50-gram servo to actuate the joints of the wrist. Here's an electrical diagram. For the most part, I'll keep it simple. This is an Arduino. An Arduino is essentially a small computer that you can program to do various things. I use this Arduino to control 2 servo boards. All this does is takes 2 pins and turns it into, in my case, 40 pins. Now, normally, if I were to use 20 servos, I would need 20 pins. So 2 turning into 20 is a great ratio that I can use to control all of my servos. And here I just have all of my servos attached to the 2 servo boards. One of the biggest hurdles that I had in this project was my wrist design. Initially, I used a disc with springs attached to it and 2 50-gram servos to actuate the wrist. Now, this isn't very authentic because it uses an axial design, which is not how the human hand operates. So I decided to prototype a new wrist, as seen here. This is kind of hard to see, so I blew it up in my 3D model. Here I have the first layer of copper bones. This first layer can sit inside the radius and ulna, which are my 3D printed radius and ulna, that I used as the forearm bones in my prototype. And the second layer of carpal bones, or my one piece, could provide flexion and extension motion of the wrist in my prototype design. Here I just show that my design properly imitates the human hand, as the first layer of carpal bones is located in a similar area as the first layer of actual carpal bones, and my second layer of carpal bones is located in a similar area as the second layer of actual carpal bones. So, for sign language, it requires every single possible movement that can be performed by the human hand. So, through all my design and development and eventually formulation of this robotic hand, I had to include all of the possible movements required by the human hand. So I'll give a quick demonstration of the hand. That's J, A, C, and K. So in reflection, my biggest hurdle was the wrist. In fact, during one of my presentations of this project, I actually burned out one of the servos as the safety check was occurring. So the amount of force and power required to move the wrist was very hard to deal with, and I had to redesign multiple times in order to get the wrist perfectly working. The other hurdle that I really faced was programming. The microprocessor that I was using, or the mini computer, is an Arduino Uno with only 16 kilobytes of storage. For those of you that don't necessarily know what storages are in relation to other things, this is like a tenth of a high quality picture. That's how much storage I was able to use in this project. And initially, I was maxing out my storage the entire time. So I had to really learn how to code properly and compress my code in order to fit it onto such a small device. Any questions or comments?
Can we show more on the hand?
Sure, I'll do your name for you.
Oh
Oh my god.
This ass. That scared me.
This is
Get out of your way. So that was A, L, I. Any other questions? Wise.
And you spoke well.
Questions?
Okay, 13:14 total, 13 minutes, 14 seconds. I liked the demonstration. I think at the end, it would be better to try and summarize everything, tell the audience why this is important and how it will help. So you did that in the beginning.
Yep.
Do it again at the end. Let's see. So also, why was the description of these movements important? So it might be worthwhile to demonstrate how each letter uses all of these different movements, abduction, adduction, things like that, flexion, so that you have to then begin with those design restrictions.
As an audience member, would you prefer that before or after I go over the structure of the hand, like the
I
anatomy?
think that should be before, because that gives you some context as to why you actually need to look at the anatomy. Does that make sense? Anybody else?
Are there, in like sign language, I'm not sure, are there like letters or things that you have to do with more than like the wrist in a hand?
Yes. So, in the future, if I wanted to perform words and signs and phrases, I would need to use arms to do that. I kind of ran out of time in order to build those structures, so I decided to just go with a hand that could perform all of the letters.
Cool.
All right, thank you.
That was so good.